Thanks for coming to my talk. I'm Mark, and I'm working with Pivotal in the Spring Data team. And before we dive into what's under the hood of Reactive Data Access, two things we have to, I think, to clarify first. So who of you has used already reactive technologies, Reactive Data Access? Cool, quite a few of you. For the others, this isn't an introductory talk, but rather what really happens when you use reactive technologies. So that was the first thing. And the other thing, thing is, what happens after this talk? After this talk, we are getting a couple of beers. And the thing between you and the beers is me. And the problem with that is I'm keeping off you from your beers, so which makes you perhaps upset. So we have to fix that. Not really burning me, but jumping right into the topic so you can happily enjoy your beers. So let's take a look on the reactive topic from Spring side. So what we provide from a Spring perspective are several Spring Data modules. And these are a couple of them, and some of them are reactive and some aren't reactive. So basically what we have reactive support for is Redis, MongoDB, Cassandra, and Couchbase. The other modules like Elasticsearch, Geode, JPA aren't supported in a reactive way yet. And the reason for that is actually quite simple. There are no reactive drivers for that. And what this really means for having a reactive driver will be part of this talk. If you have any questions, feel free to raise your hand, and if we can clarify your question immediately, we can do so. Otherwise, just grab me afterwards. And the one thing which came to our attention is, well, in the real world, a lot of people are using relational databases. So that's a majority of the database technologies, persistent technologies, which is used. But you see, maybe you noticed that JPA disappeared. So why is that? Well, JDBC and JPA are the most common technology, yet there isn't reactive support for that. And this might raise the question why this is. And the reason for that is quite simple. JDBC is a blocking API, which requires an imperative execution model. So one thing happens after another in a blocking waiting style. So one operation has to complete first until the next can start. And this doesn't really fit into the reactive thinking. So relational databases come typically with blocking drivers. There are a few exceptions, but they are very rare. That's one reason. Another reason is relational databases aren't really the best fit for a reactive data access. There are a couple of reasons besides the driver story why this is. One of the most compelling reasons is that you have a limited scalability story with relational databases. So if you try to set up a cluster of MySQL or Postgres or even Oracle, you have to spend a lot of time, a lot of money into that, and still you have some limitations imposed on that. While in the NoSQL world, scalability and in both directions, horizontal and vertical, is the standard mode of operations. Therefore, do scale NoSQL databases much better, and you can immediately add new machines if you feel that there is a demand for that, which really fits better to the idea of very efficient resource usage to easily scale up and down services. You don't have that necessarily for relational databases. Another thing is the resource synchronization. So a common thing which is used in a relational database world is connection pooling. And there are, I guess, theses, papers on how to calculate pool sizes, but still, that's a limited resource. You can't have endless connections to your relational database servers, but with the approach the reactive way is taking is you want to eliminate that bottleneck, but you can't really do so. So there you go into resource synchronization because of connection pooling. You can't really multiplex on connections. And I think the most compelling and most heavyweight reason why relational databases aren't a good fit is, well, transactions. What we try within the Spring framework to do is to use resources as efficiently as possible. This means non-blocking algorithms, removing locks where we can, no synchronization, or at least minimize synchronization. But what happens with asset transactions, and especially the isolation bit? Well, with isolation, you move the lock from your application into your database. And what happens there is that when two concurrent writes happen at a certain time, the second write has to wait until the first one is has completed. And this, again, isn't something which plays well in a reactive world. But still, there are possibilities, because, as I said, the reality is this one, that most of our persistence technology is relational. And we need to find an answer for that, how to deal with these particular questions. And as of now, there are two possibilities. The one is called ADBA. That's an effort driven by Oracle, and the acronym stands for Asynchronous Database API. The other one is R2DBC, which is an effort driven by Pivotal, so company I work for. And this tries to leverage Reactive Streams-based API. So ADBA was announced, I guess, 2 years ago on Java 1. And it is an asynchronously built database API that uses completable future under the hood. So then you can use your relational database. And when you do I/O operations, you get in return a completable future. This completable future completes as soon as the database responds to you, and you have a non-blocking and asynchronous way to communicate with your relational database. However, from a reactive streams, and especially from a streaming perspective, this isn't ideal, because you do not only want to eliminate the blocking aspect, but you also want to optimize for latency. So, which means you want to process items as soon as possible and as early as they arrive. So imagine, well, you have a cursor where you read data, and the first chunk already arrived and could be decoded, but you are enforced to wait until the whole result comes back to your client, and only then you can start really with the processing. That was a reason enough for us to do an API experiment, which is called R2DBC, or Reactive Relational Database Connectors. It's an API experiment based on reactive streams. And one of the main drivers behind the reactive streams specification, David Carnock, who also actively works with RxJava, came up with an API proposal. And we started to pick up this API proposal and write a reactive driver on top of that, which is currently supported for a Postgres database. However, it's fully reactive. It allows you to process data as soon as possible, and it's much more powerful from our perspective to adopt and leverage the reactive idea within relational databases. This is something that we could imagine to happen in a future Spring version. And we do not really know whether ADBA is the thing which will make it into Spring, or R2DBC will be the thing which will make it into Spring. But we will have to come up with some idea to also address the majority of what is used as persistence technology. So there's a GitHub repository. I think you can't read the link, but that's not an issue right now. I will upload the slides after the talk, so you can go over the slides then afterwards offline and look up the link. So let's take a look after we clarified the relational data piece. What changes between imperative and reactive data access from a query behavior perspective. So you will see a couple of these diagrams. This gray line is the transport. So not necessarily a TCP connection, but everything that's related with the transport. And this happens all over time. So for synchronous database access, as we are used to it today, we typically issue a query against the data store. This query takes some while until it's processed on the data side, until it arrives on the database server. And while this is all happening, we are spending CPU cycles. And we are basically burning these CPU cycles because the thread which we are using is blocked and cannot do any further work, so any more sensible work. Well, then at the time the database or remote service decides to come back with an answer, we start processing that. Maybe we go again to the database, spend CPU cycles, and so on and so on. And I guess you get the idea. With from a reactive standing point, we might have a similar access scheme that we go to the database, but this bit isn't any longer blocked. So that's a major difference between imperative and reactive data access, that as soon as a request is written to the transport, the originating thread is free, and it's not waiting any longer for a request, but rather it can process subsequent requests from other incoming work or process even responses from a driver, and it can do its work as fast as possible without really awaiting the response incoming from a database. And once the data store starts to respond, the typical use case is that we start to process the data, decode the data, and emit the data directly to the application without the need to await the full completion. So we do not need to wait until the very last chunk of your query streams in, but rather immediately start with the processing. And that's a huge advantage over what we can do today with the imperative access. And that being said, imperative and blocking isn't bad. You can get very, very far, but when you decide to use your resources much more efficiently, or if you run out of resources, basically, then reactive can be a very good answer to address that problem and create new problems. That has also to be said. Well, let's continue with a query scheme. So the reactive stream specification has a concept built in which is demand and back pressure. So you communicate from your application process to your driver or I/O layer how much data you want to process. And based on this knowledge, the driver can do smart things. For instance, it can go back to your database and request the next chunk. And this can happen before you even process the very last bit of the chunk that came in. So you get a notion of smart prefetching here. While you're still busy processing data, the driver is fetching data, and another chunk for you, and then comes back, which reduces, again, the latency until you are able to process the next chunk. And this goes by and by until you have processed the last chunk, and there you go. And then you really you use the benefits from reactive data access. So what's the difference beyond that, what we have seen? Well, reactive drivers require a threading infrastructure. This is because reactive data access needs an active component. In the imperative data access, you typically have a thread, and the thread is issuing all the I/O work. But in a reactive world, the thread just writes to the transport and then comes immediately back to do other work. And somebody has to listen on responses and process them and provide you with a thread that does the response processing. So this means that you will see different threads being spun up by different drivers that do not necessarily belong to the thread pool or the execution infrastructure that is provided by your framework. Another thing that changes with Reactive Data Access is how we handle timeouts. And this is an essential bit because not every driver supports that, and the way how drivers support that is very different. So in synchronous API usage, we might be used to the notion of read timeout or the socket timeout. And the idea behind that is to protect the client with a particular timeout, to not block forever the application, but to come back once either the timeout is exceeded or when data comes in. So this also means that if you have multiple I/O operations, this read timeout does not bound you with the notion of how long this particular request takes, but how long a particular read may take up. And if you have 10 reads and the system is slow, you may experience the timeout 10 times, for instance. In a reactive world and a non-blocking world, we don't have any longer this read timeout notion because we are not blocked. So the only thing we can apply there is specifying a timeout per operation. And this is really different from the way of thinking how we thought about a blocking timeout on a socket level. While the socket level timeout can occur multiple times, the timeout for a particular command specifies the exact duration this command may take. This gives us, I think, much more control over the things we actually want to achieve, but still it's a difference to the things we were used to. So another thing which is also true is that we need an active component to track these timeouts. And as I mentioned, some drivers do have that and some others don't. And if you look on the optimization bit, tracking timeouts has a certain cost associated with. So you can decide whether you want to take this cost or not. But again, this is something which is deeply nested into drivers. So when talking about reactive drivers, we have to make clear what this really means. A reactive driver is not anything, but that's a piece of software that guarantees you a non-blocking behavior from end to end. So from writing a request to your data store until you process the final request. If you have a blocking component in between, that's not a reactive thing. If you put a blocking call on a thread pool, that's not a reactive driver. You just move the problem to a different facility, but you don't really solve that. Reactive drivers typically use Java NIO or Netty under the hood, which also uses then Java NIO. And these tools allow you to minimize the resource usage by providing only the necessary and essential parts. So when you configure a thread pool of say 4 threads, which is sufficient for a lot of examples, then these 4 threads are not blocked, never ever, and these threads are used as efficiently as possible, yet they are there. Another thing that also changes with a reactive driver is the way how connection pooling works. Today, when we look at a JDBC data source, we have a GET connection there, and once we retrieve a connection, we can close it. And what happens under the hood of pooling implementations is they try to acquire a connection and give you one back when a connection is there. When the pool is exhausted or needs to be refilled, then the pooling implementation connects your server in a blocking way. Maybe it issues some testing statements to validate the connection is there. And until that time, your thread that tries to acquire the connection is blocked. That's different for non-blocking pooling implementations. All these things happen on an outside thread, And typically, you get some sort of synchronization data structure, say a completable future, and this one completes as soon as the work for the pool is done. However, that's a different implementation to what we have today. And finally, what's also a prerequisite to make non-blocking pools work is a non-blocking and connect method, obviously. When we take a look what happens inside the driver itself, then we will recognize that's not just only a black box, but it allows us look what happens inside of it. Typically, when you deal with NoSQL drivers, you have some piece of software between your request and your response. And in this piece of software, you have to accomplish multiple tasks, which again needs to be performed in a non-blocking way, like server selection. So if you use MongoDB and use read preferences, which server to use. You typically queue commands that you can issue multiple commands as soon as possible. And these commands are written then to the transport as soon as the driver is ready to write them out. And then basically the thing your main driving thread does is over, and the thread goes back to some thread pool, is released, and can do different work, for instance, when receiving data. So that's something which is provided typically by the driver itself, that it starts to decode the incoming payload. It starts to buffer the data that's retrieved from the database. And once everything is received and processed, the driver completes your request. I've spoken earlier about demand and back pressure. And the truth is, our databases are not aware of such a concept. So reactive drivers have to take this fact into account and not fetch endless data amounts from your database server, but rather react to the notion of how much demand you have on your application, and fetch iteratively data then from the database. For data stores which work with cursors, this could mean, okay, I'm going to fetch the very first cursor, read all the data, buffer it locally, and then when I see there is still demand and my buffer has a certain amount, reached a certain level of how full or empty it is, it will go again to the database and then fetch the next bit of data to not overwhelm your client, but rather to adapt to the performance behavior your application exposes. So let's take a deeper look on the NoSQL drivers we are currently supporting, and let's start with MongoDB first. So MongoDB provides two reactive drivers. One is the RxJava1 driver, and RxJava1 is end-of-life, so we don't need to consider this one too deeply. The more interesting one is the Reactive Streams driver, which natively works with Project Reactor since it's implementing the very same API. The Reactive Streams driver, and basically both reactive drivers on MongoDB, are actually a facade over the asynchronous driver. So MongoDB provides two real driver implementations. The blocking synchronous one, that's, I think, the one you typically use. And then the asynchronous one, which uses Java in I/O and callbacks. And what MongoDB did there is they wrapped the asynchronous driver and provided a reactive streams facade on top of that. The MongoDB driver tree also attached the lifecycle of a cursor to a particular publisher. So a publisher is the thing that you get when you describe a query. So fetch all records from a particular collection. And in an imperative world, you have to maintain the lifecycle of the cursor yourself, which means that you have to close it after you have used that. The nice thing here in the reactive world is that we get signals when data emission starts and when the emission completes or terminates with an error or gets cancelled. And these signals are reassembled by the MongoDB driver into the cursor lifecycle, so are no longer required to close the cursor, but that's a task that the MongoDB driver does for you. You get pluggable I/O, with the MongoDB asynchronous driver. By default, the driver uses plain Java NIO with a thread pool attached. If you want to use SSL, however, or feel more comfortable with Netty, then that's an option also you can take. You can plug in Netty to use much more efficient buffer pooling, to use SSL. And if you are using Netty anyways, because, well, when you are using Webflux with the default configuration, then Netty is out of the box there for you. Then this is a very sane option to consider. And finally, MongoDB uses a connection pool to dispatch connections to multiple servers, as MongoDB's overall concept is to talk to multiple servers at the very same time, to distribute load, to materialize read preferences or write concerns. So that's all happening within the MongoDB driver. The thing that we will see now is an effect of how the MongoDB driver is built. So I mentioned earlier, the MongoDB driver, the reactive one, is just a facade on top of the asynchronous driver. And the asynchronous driver communicates through futures, and it communicates only complete results, which means that the whole result has to be received in order to process the next chunk. And that's what we also see here. When we issue a request to the MongoDB, then we are receiving the first chunk, the next chunk, perhaps that's the completion chunk. Then MongoDB starts prefetching the next chunk, and we didn't return to the application yet. So that's an interesting bit here. And once the prefetch request, the next one, is issued, only then the driver starts to emit the items it has. Although we could really start already here at this point. But I think that's an optimization the MongoDB driver team is going to take in a future version. Let's see what really happens there. Another thing to pay attention for is how we fetch data. So MongoDB uses a batch size to determine how many requests to fetch from a server. So if you're issuing a query or fetching data from a cursor, you always have to specify how much documents you want to retrieve. And this information is derived from the demand, from the back pressure, which is a very sane thing to do, because once you have this information, then you can reassemble that to reuse it for subsequent requests. So that's a cool thing. In a access scenario, the subscriber requests an amount from its publisher, or even if you have an operator in between, this demand is propagated then to the data source. But let's take a look in the context of a particular operator, which is a filter operator. So the filter operator, at least implemented from Project Reactor, is working that way that you're able to specify a predicate, and if this predicate yields true, then the element is emitted to the next operator, or even to the target, depending on what the target is. If the predicate evaluates to false, this means the element is dropped. To maintain the back pressure details, the filter operator requests another element, because when you requested 5 elements and you drop one, then you have already consumed one, 4 are in the queue, and you want to still consume 5 elements. So you have to request another one to increase the demand. Right. But this can have a severe effect on how MongoDB works and how the driver works. And let's take a look into the code, how this really behaves. So first of all, I have here a piece of code. I will also send out the links to the code after the session. I have here a piece of code that accesses MongoDB through Spring Data MongoDB. And I added a little bit of logging in here. The thing I'm doing right now is fetching all items from the person collection And we see a little bit of command logging here. We have a find operation for the person collection, no filter on it, and since since the max size for a request is int max size, we see this 2.514-ish number in here. So that's actually the maximum size that we can request. We didn't specify anything else, so that's the reason why we are seeing this number here. Let's bring in back pressure control into the game. And I'm using the step verifier and specifying a number of items I want to retrieve. Step verifier is a class from the Reactor test project, which allows us to test reactive streams components. And along this creation of this step verifier, I'm specifying, okay, give me the next 10 items, then await until I have received these items, and then request another 10. So when we issue this request, then we will see that we will have multiple requests to MongoDB. So the batch size changes to 10, obviously, because the MongoDB driver resembles the back pressure detail into the batch size itself. And since the cursor has much more elements on it, we are fetching the data in a second step to get even more elements from that. Right. So until here, everything is cool. Now let's bring the state filter operator into the game, and I'm filtering here on the name length. So that's an easy thing. I'm doing a client-side filtering of the data. What could possibly go wrong? Well, let's see what could possibly go wrong. If I start executing this, whoa, what's this? We're seeing a lot of these get more requests. And the reason for that is, well, filter is dropping elements. So it's not emitting an element that does not match my predicate, and requesting an additional element. And what really happens in here is that the driver sees, okay, well, my internal queue is empty. Let's go to MongoDB and fetch another set of records. And we see a varying number of demand. And a lot of requests that happen here to my MongoDB, and this is quite a surprise. That's not an obvious thing. You would immediately recognize during testing or during development time, but rather when there's a lot of traffic on your production system, and this isn't really something you want to discover at that late time. So probably that's the reason why you're sitting around here in the audience. So what can we do for that? Well, the one thing we can do is to wait for the new driver version, because that's got addressed by the MongoDB driver team. However, it's not yet available, and I want to show you a different possibility how to deal with that particular issue, and that's a built-in operator in Project Reactor. Here we have another operator, which is limit rate, and what limit rate does is it allows us control over batching with the possibility to cap the batch size at a certain amount. So I used here limit rate 20. Before I'm using the filter operator, and this means there happens some sort of control over how many items are prefetched and how many items are requested. Executing this piece of code reduces the number of MongoDB calls, so we see a more or less consistent amount of items which are requested. And in case if you're wondering, the limit rate operator does some calculation internally to fetch to a number of records or to communicate the demand that is more or less what you're supposed to fetch. So putting this in front of the filter solves my problem. Putting that after the filter, again, comes within the problem, or recreates the problem. Hello? Recreates a problem? Recreates a problem? No. It's that's fine. That's fine. Well, maybe I screwed up the demo. Nevertheless, actually ordering matters. I had it earlier. I was able to recreate it earlier, and you should pay really attention to that, because depending on the operator you're using, the back pressure detail may be recalculated, and what you want to have control over is actually the batch size, and you want to control the batch size as soon as possible. Yes, question?
Yes, in an SQL world, you would do this filtering on the server. Is it not possible here?
It is possible, but it was much more fun to show what happens if you do it on the client side. Cool. Then, after having a look on that area, I want to tell you about some features that are exclusively available only for the reactive support. Currently, we support tailable cursors for MongoDB through repositories. That's a possibility to stream endless data. So as soon as items are inserted in a kept collection, these documents are emitted to the client, and you can build up messaging scenarios with that. This functionality will be also supported by the imperative implementation of Spring Data MongoDB in a future version, but as of now, only the reactive bit is supported. And what we have also support for is change streams. So this means you can watch what happens on the whole MongoDB database by leveraging the MongoDB oplog. So that's the source for replication operations, and also stream all the things that are happening in terms of updating objects, updating documents, inserting, deleting, and a nice hook to build event-driven use cases. The next driver I want to present you is for Redis. And for Redis, we have fully reactive driver, which means that's a true native reactive driver without the bottleneck of the need to synchronize the whole request. It's built on top of Netty and Project Reactor. So if you interoperate with that facility, you get true Project Reactor types. It's wrapped also within Spring Data Redis, which gives you a little bit more control over encoding, decoding, exception translation, and these kind of aspects. Typically, it uses a singleton connection because Redis is a single-threaded database. But if you want to, you can also use pooled connections. That's typically the case when you are dealing with Redis transactions, with blocking Redis commands that block the connection. When we take a look how we receive our data over time, that's this way. You send a command to the server. The server starts processing the request. And as soon as the very first chunk comes in, we start decoding on the response and decode the whole chunk. And in that time, the driver is able to receive the next and subsequent chunks, which helps to reduce, again, latency and process items as soon as they are received. And Redis is a typical data store where you would store a lot of data, so gigabytes of items, which might be even more what you can have on your application side. And to be honest, you don't want to eat up all your memory with a single Redis command that's issued by a single user, but rather to consume data in a much more efficient style. And the streaming approach of reactive streams allows you to do that because you get hold of one element at a time, and you don't have to synchronize all the results within a list or a collection or something like that. Specifically for Spring Data Redis, we are using byte buffers instead of byte arrays to improve allocation and reuse of memory that we are using to do serialization on. We can provide pooled facilities for these buffers to reduce, again, memory pressure, GC pressure. One thing that is quite specific to Redis is that it responds quite often in an imperative world with a null value. and null values, if you're familiar with the reactive stream spec, are prohibited. So there we have to get creative with either providing data structures like optionals, or leverage the idea of not emitting any elements. And that's again something which is a difference in comparison to imperative data access. And one other neat thing which comes along the fact that the driver is fully reactive, the driver suspends reads when there is no demand. So this might sound not as a big deal, but in fact, what the typical driver is doing, it is consuming all the data which comes over TCP or another transport, and this is eating up buffer space. And because we know the demand, we can stop reading from a channel, which leaves the data on the transport, and this can also propagate up to your Redis server, where we attempt to propagate the notion of back pressure to the server itself, which is called TCP back pressure. So that's the idea behind that. Cool. Next one up is the Apache Cassandra driver from DataStax. It's, well, not a reactive driver per se. So if you take a look at what happens on the DataStax side, you will see the DataStax driver, Java driver, which has an asynchronous interface, meaning that you are communicating through futures. And we decided to pick up on that loose end, because everything else works really smooth in terms of a reactive integration. So what we built is a reactive bridge on top of the Cassandra driver, which lives in the Spring Data for Apache Cassandra project. We are using the DataStax driver, which is Netty based. There are also a couple of other drivers, like the asyntax driver from the Netflix folks. But we decided to stick with the DataStax driver, as that was already built into Spring Data for Apache Cassandra. Cassandra requires, again, connection pooling, because it's interacting with multiple hosts at a certain time. And there you have to maintain multiple connections to your hosts. When we take a look again here at the query by time diagram, we will see the limitations that come because of the wrapping of results into futures, that we have to await the very last bit of the response before we can start processing the response. However, we picked up here on this loose end to improve, at least on the prefetching side, that we start to emit items really as soon as possible and issue the next request to fetch the next page of the cursor as late as possible, so that we can benefit from the processing side in client applications. There's an outlook to that. DataStax is working on a driver 4.0, which is currently in the works. It should have been published by April. Yeah, it's not there yet, but it will feature reactive execution support, which means that it will be, again, a native reactive driver core, which allows us to adopt more smoothly to the specifics of this API. And emit items as soon as they are processed. That's a link to the GitHub repository and the Jira ticket they have. And if you're interested in that, you can follow these links and leave your vote in the issue tracker. And the last one is Couchbase. Again, a fully reactive driver. It's built, however, on Netty and RxJava 1. And I think you will recognize quite quickly the only constant here. A lot of drivers are built on top of Netty. And this is, again, something which is a dependency magnet. And from my personal opinion, I'm not quite sure whether that's a good thing or a bad thing. I think the time has to prove how things are. It follows multiple connection schemes, as Couchbase has multiple ways how to interact with the data. It's a key value store. It's a document store. You can do full text indexing, and this has, again, different schemes, how the driver interacts with the database, and how responses are fetched. Sometimes they are synchronized until the last bit is received and then start emitting items. Sometimes the responses are streamed, and this really depends on the functionality you are using. So let's step over that. I think we've seen that already. So I mentioned RxJava 1 in the context of Couchbase. That's end of life. There is, however, no decision yet what the future of this driver will be. It is likely that Couchbase will migrate over to RxJava 2, but there is no decision yet. If that's an essential bit for you to know when there will be some movement, go to the issue tracker and ask these folks. The integration for Spring Data Cassandra, for Spring Data Couchbase is already there. It's adopting the RxJava parts and giving you the full experience of either using RxJava or the auto-adaption mechanism on repository level, where you can declare even reactive stream types to interact with Couchbase. So sometimes we get into the situation where we have a reactive driver, but we want to do something in an imperative style. So for instance, writing an initializer for data. So we want to prepare our database, or we want to clean up the database. And traditionally, that's something that you would do in an at post construct callback. So until we get there, we should first clarify that blocking in an imperative world is the thing you would expect. That's the most natural pattern that you follow, and that's the way how things work today. So that's a really good thing. But as soon as you start blocking in an imperative runtime, then things can get really hairy. And to be honest, every time you call .block, a kitten dies. So that's a thing you should be aware to not do that. I will come to that, why this is. So that's an example component here. I have a component with a post-construct block. I'm using the reactive MongoDB driver. So the most natural option would be for me to reuse it across my whole application. And since I'm required to wait for the result of this operation, which removes all items from a person collection, I would call .block. You see, one kitten is already dead. We shouldn't do that. And the reason for that is the threading or execution model which lies below of this driver. So typically, when we are talking about Netty, Netty has the notion of an event loop. So an event loop is a single thread that spins all around until there is work to do. And this event loop is fed by a work queue. So you put work items into that queue. That's picked up by the event loop itself. The event loop does a callback to the work item, typically a runnable or a callable. And there happens then the thing we usually do within our application. So that might be database calls, file I/O computation. Once we are done with that, and let's stick with the example of the database call. We request data from the database. We need to register a callback to then process also the response in some way. So what happens here is that we add another element to the work queue. And once this is done, we are happily returning because we are not awaiting the response. That's a cool thing about this event loop model. However, when we start thinking in the blocking way, and we have a piece of work that contains blocking code, we again get called by the event loop thread. We potentially register a callback because, hey, we are interacting with a reactive driver. And then suddenly we come to the line of code where we wait for the completion, for the request completion. That's the line where you call .block. And when we wait for completion, then we are blocking the thread. And by blocking the thread, this means this thread cannot progress any further. So the thread is busy with doing our work. We have a request callback here, but the thread never gets there. So I think that makes it clear why you never should block within a reactive runtime. And the simple answer for that is, well, if you are dealing with initializers, like I've shown before, use the imperative driver. Although it can mean that you add additional connections, but that's the safe bet and the safe way, and it's much more safer, because when you have one single block call in your whole application that's running on, for instance, a netty with webflux, you can break with this single line of code your whole application. And that's why you shouldn't do that. So, threshold, not block. That being said, I think it's time to make my promise true to leave you out for the beers. It was a pleasure to present in front of you. Have a great Spring I/O. If you have questions, grab me and enjoy your evening. Thank you.